Hello and welcome back to Engineers Olympiad. Computation of peak flood flow and determination of design discharge is topic for today. So let's start. Since we are dealing with hydrological and hydraulic design of bridges, wherein we studied in the previous video lecture that in hydrological design, we have to assess about the amount of water that is going to come on that particular bridge site where we are designing a bridge. So we have to calculate this thing, our design discharge, all right? The maximum discharge which a bridge across a natural stream is to be designed to pass can be estimated by many methods, and I'll write them here. One being by using one of the empirical formulae applicable to that region where we are designing our bridge. All right. The maximum discharge which a bridge across a natural stream is to be designed to pass can be estimated by many methods. The first one being by use of empirical formulae applicable to that region. Second one is by using a rational method involving the rainfall and other characteristics of that area. By using a rational method involving rainfall and other characteristics of that area. Rainfall and other characteristics of that particular catchment area of that bridge site. This is the second method for determination of the maximum discharge which a bridge across a natural stream is to be designed for. All right. Third one being by the area velocity method. By the area velocity method. Area velocity method using the hydraulic characteristics of the stream such as cross-sectional area and the slope of the stream. All right. By the area velocity method, which makes use of the hydraulic characteristics of the stream, such as the cross-sectional area and the slope of the stream. Fourth one is by unit hydrograph method. Unit hydrograph method. We make use of this method to determine the maximum discharge which a bridge across a natural stream is to be designed to pass. All right. Next one, let me rub it first. First one was by making use of empirical formula applicable to that region. The second one being by using a rational method that involves the rainfall and other characteristics of that particular area. Third one being by making use of the area velocity method. We make use of area velocity, and in that method we take hydraulic characteristics of the stream, particularly that of cross-sectional area and slope of the stream. The fourth one was the unit hydrograph method. The fifth one is from any available records of the flood discharges observed at the bridge site or at any other site in its vicinity. All right. From any available records of the flood discharges observed at the bridge site or at any other site in its vicinity. In the vicinity of the proposed bridge construction site. All right. So these were the methods by which we make use of various factors like characteristics of the area by making use of rainfall and other characteristics. We make use of the rational method. We determine the design discharge or the maximum discharge. Then we make hydraulic characteristics. We make use of hydraulic characteristics of the stream, such as cross-sectional area, slope of the stream, and we use area velocity method and go on calculating our maximum discharge, like on with empirical formulae which have been developed for various regions. We'll go through that also by unit hydrograph method, or by making use of the available records, because flood, whenever they occur, they're always being recorded vis-a-vis HFL, etc. So by making use of available records of the flood discharge observed at that bridge site or at any other site in the vicinity. All right, so we can make use of these methods and go on calculating our maximum discharge. Then the important thing is design discharge. All right, what shall be the design discharge for going on calculating the hydrological design of a bridge? All right, design discharge. The design discharge may be taken as the maximum value obtained from at least two of the methods. All right, we can make use of any of the two methods, and the maximum value among us the two will be taken as the design discharge. But it must be noted that freak discharges of high intensity due to failure of a dam or a tank constructed upstream of that particular bridge site need not to be catered for. Any freak discharges of high intensity which occur due to failure of a dam or a tank constructed upstream of that bridge particular site, they need not to be catered for. All right. And from consideration of economy, it is not desirable to aim to provide for the passage of the very extraordinary flood that may ever happen at a particular site. No, we don't do that. It is, however, adequate that we design for a flood occurring once in 50 years, and we ensure or make sure that rarer floods be passed without any excessive damage to the structure. All right. So how do we calculate the design discharge? We make use of any of the method that we already discussed, and we take at least two. Then we take the maximum value amongst that two, and that we take as our design discharge. All right. Let me drop it first so that we can move ahead. This is about how do we go on calculating the maximum discharge. All right, and how do we take our design discharge after calculating the maximum discharge by at least two different methods. All right. Now, this prediction of peak discharge rates or synthesizing a complete discharge hydrograph. What is a hydrograph? It's a graph between discharge and time. Hydrograph is a graph between discharge and time, and it tells us how the discharge of a river changes with time at a particular location. All right. So this prediction of peak discharge rates or synthesizing complete discharge hydrographs for use in the design of minor and major bridge structures are two of the most challenging aspects. All right. These are very challenging. Our prediction of peak discharge rates or our synthesizing of discharge hydrographs for use in the design of minor and major bridge structures are very challenging aspects of bridge hydrology. Because our basic motive and essence of bridge hydrology is to calculate the amount of maximum discharge that will pass under that bridge construction site proposed. All right. So this is very challenging, and generally a hydrologist is required to provide peak rates of discharge and stages at a designed frequency, or he may even synthesize a complete discharge hydrograph for a design storm. All right. So this hydrological design aspects of a complete bridge structures are considerably more complex than that of a small culvert or a bridge, small bridge or a culvert. Very obvious that hydrological design aspects of a complete bridge structure is very complex than those of a small bridge or a culvert. And this economic selection of waterway from various possibilities, it dictates at the final design, right? Let me rub it first and then I'll explain it. A hydrologist needs to synthesize the peak rates of discharge by way of making or synthesizing a complete discharge hydrograph for a particular storm. And the hydrologic design aspects such as economic selection of waterway, that means our hydraulic design from various possibilities, it dictates our final design of the bridge. And it is function of various things. Like we have to take various things into consideration. The first one being degree of protection to be provided, project economy, very important. That is very important. Project economy, agency policy. Let me write it over here. Agency policy. And construction standards. All right. The economic selection of waterway from various possibilities dictates our final design and is a function of various things like degree of protection to be provided, project economy, agency policy, and our construction standards. All right. So this was about how do we calculate the maximum discharge and the design discharge, and you got an insight into all this. How do we make such calculations and how important it is for the hydrological and hydraulic design of bridges. All right. Now we'll go on studying one by one these methods. The methods that we just discussed that we make use of to ascertain the maximum discharge. And then only we can go on calculating our design discharge. For that we have to make use of at least two of the methods, and the maximum value will be taken as the design discharge. All right. Moving on, the first method is use of empirical formulae. All right. For finding out the maximum flood discharge, certain empirical formulae have been developed by many eminent hydrologists and engineers over time. By past observations in the similar areas, and these formulae directly give us the maximum flood discharge of a river. Which formulae? The empirical formulae. All right, these have been developed by eminent hydrologists and engineers over time, and they give us the estimation for the maximum flood discharge of a river. All right, and the empirical formulae for prediction of peak discharges are employed only when sufficient data is not available for detailed and precise analysis of the catchment response. All right, we make use of these empirical formulae for prediction of peak discharges only when sufficient data is not available for detailed and precise analysis of the catchment response. And one of the main drawbacks of these, we'll study about the drawbacks of empirical formula after we complete them. But here I'd like to tell you that one of the drawbacks of these empirical methods is that each formula is applicable only to the catchment for which it is developed. All right. And the general form of the empirical equation, general form of empirical equation is Q is equal to CA raised to the power N, where Q is peak discharge, A is area of catchment, C and N, these are the constants which absorb the storm and the catchment characteristics. All right, and they are arrived after taking certain factors into consideration, like that of the basin characteristics and the storm characteristics. Let me write it down here. Basin characteristics and storm characteristics. In basin, we take into account the area of that basin, the shape and the slope. And storm, the first one being its intensity, the second one being its duration, and the third one being its distribution. All right. So this is the general form of the equation of the empirical formulae from which we can calculate the peak discharge of that particular area. All right. And the general expression is Q is equal to CA raised to the power N, where Q is the peak discharge, A is the area of the catchment, and C and N are the constants which absorb the storm and catchment characteristics. And these constants for the catchment is arrived, this is arrived after taking the following factors into consideration, like the basin characteristics and the storm characteristics. In basin, we take its area, shape, and slope, and storm, we consider its intensity, duration, and distribution. All right. So this is the generalized form of the empirical equation used for calculation of the peak discharge rates. All right. Q is equal to C A raised to the power N. Now we'll study about empirical formulae which have been developed for particular regions and have evolved over time. The first one being Dickens formula. All right, Dickens formula. Dickens, for the first time in 1885, made an attempt and derived a formula of the following form to predict what? The main aim, prediction of the maximum flood on the basis of the studies which he conducted on the Indian rivers. Very important to note. For determination of the waterway of the bridges, and he developed his formula as this, wherein our generalized expression was Q is equal to C raised by N, where Dickon gave the formula wherein he conducted his analysis, his studies on Indian rivers, and he gave us this formula. Q is equal to CA raised power 3 by 4. And this formula is applicable to catchments in central and north India. The Dickens formula for estimation of the maximum flood discharges is based on the equation, which is Q is equal to CA raised by 3 by 4, and this formula is applicable to catchments in central and north India, and this constant C, it varies from 2.80 to 5.6 for plain catchments, and C varies from 14 to 28 for mountainous regions. For mountainous regions, all right. So the Dickens formula is an empirical formula, and Dickens, for the first time in 1885, he made an attempt and derived a formula of the following form: Q is equal to C A raised by 3 by 4, after he conducted his studies on Indian rivers, and he gave his formula. But the point to note is that this formula is applicable to catchments in central and north India, and this constant C varies from 2.80 to 5.6 for plain catchments and from 14 to 28 for mountainous regions. But recent studies were conducted, and to make Dickens' formula applicable to different parts of India, not only to the central and the north India, the constants were suggested, and I'll tabulate them here. Dickens constants for different watersheds. Dickens constants for different watersheds. All right. Here I write type of watershed, and here Dickens constant. Since initially it was only applicable to the regions of central and north India, then to make it applicable to different parts of India, not only to central and northern region, we have certain constants for different watersheds, and I'll write it and you go on noting. First one, bare catchments. Bare catchments covered with precipitous hills. All right, bare catchments covered with precipitous hills. Dickens constant C varies from 19.6 to 28.0. Second one, catchments with hills on the skirts with undulating country. Catchments with hills on the skirts with undulating country. For that, Dickens constant, undulating country, Dickens constant varies from 14 to 16.8. All right, let me rub it, and then I'll tell you about two other types of watersheds. The third one is type of watershed is undulating country with hard indurated clay. Undulating country with hard indurated clay. This is type of watershed, and the Dickens constant C herein varies from 11.2 to 14.0. The last type of watershed is flat, sandy, absorbent or cultivated plains. Flat, sandy, absorbent or cultivated plains. Cultivated plains, all right. And here in this type of watershed, the Dickens constant varies from 2.8 to 7.0. All right. So this was about the first empirical formula, the Dickens formula, which he developed in 1885 after conducting studies on the Indian rivers. And the formula he gave is Q is equal to C A raised to power 3 by 4. Initially, this was only applicable to the central and the north India, but now recently, to make it applicable to different parts of India, certain constants for different types of watersheds have been suggested that we had tabulated here. And this formula gives us, or this predicts the maximum flood discharge of rivers. All right, so this was about the Dickens formula. The next empirical formula is Ali Nawaz Jang Bahadur formula. Jang Bahadur's formula. All right, so this is the second empirical formula for prediction of the maximum discharge, and this formula involves a logarithmic function of areas as the exponent. And this hydrologist or engineer, Jang Bahadur, he was of the opinion that the formula to be applied should be simple but rational without involving much of the judgment on the part of the hydrologist who is selecting the coefficient C. So he gave us the formula, which is Q is equal to C 0.368 A 0.925 minus log of 0.386 A, or you may even rub it, divided by 14. All right, and the value of C is, it is 49 for regions in southern India, and it is how much? It is 60 for regions in northern India. All right, so this is the next formula, empirical formula for determination of the maximum flood discharges. And the hydrologist which developed this formula is Ali Nawaz Jang Bahadur's formula. This is known as Ali Nawaz Jang Bahadur's formula, and this involves a logarithmic function of the area as the exponent. And Jang Bahadur, he was of the opinion that the formula to be applied should be simple but should be rational without involving much of the judgment on the part of the hydrologist who is selecting the coefficient. And he gave us this formula, wherein C is 46 for the regions in southern India and it is 60 for the regions in northern India. All right, moving on. Next one. The next empirical formula that we are going to study here is the Rice formula. All right. Rice formula. Wright modified the Dickens formula for application to catchments in southern regions of India. Since we studied during this Dickens formula that it's applicable to catchments in central and northern India, so Wright modified the Dickens formula for application to catchments in southern parts of India, and the modified formula is Q is equal to CA raised power 2 by 3, where in Dickens formula it was Q is equal to CA raised power 3 by 4. So Wright modified the Dickens formula for its application to the southern regions of India, and he gave us the formula Q is equal to CA raised power 2 by 3, where A is area of the catchment in square kilometers. You have to be quite mindful of the units while we'll do the numericals. Each and every formula is based on a particular unit for which it is determined. In rational formula we'll study about that. A is equal to area of catchments in square kilometers. Please note. Next is C. It is 6.74 for areas up to 24 kilometer from the coast, and it is 8.45 for areas in between 24 to 161 kilometers from the coast, and C is 10.1 for hilly areas. All right, so this is about the Rice formula. The Rye modified the Dickens formula for its application to the southern parts of India, and he gave us the empirical formula for determination of the maximum discharge, which is Q is equal to CA raised power 2 by 3, where A is the area of catchment in square kilometers and C is 6.74 for all such areas which lie between or up to 24 kilometers from the coast, and it's 8.45 for those areas which are at a distance of 24 to 161 kilometers from the coast, and it is 10.1 for the hilly areas. All right, so this was about the Rice formula. Next one is English formula. English formula. All right, so this is our fourth empirical formula, English formula. English studied the available hydrologic records of catchments of erstwhile state of Bombay and of a fifth catchments outside the state, and he arrived at a formula which is Q is 124A divided by A plus 10.24. This is for all such areas which are less or equal to 130 square kilometers, and Q is 124A divided by the root of A plus 10.24 minus 16. This is for area just more than 130 square kilometers. All right, so this is about the English formula, and English studied the available hydrologic records of catchments of erstwhile state of Bombay and all other catchments outside the state as well, and he arrived at a relationship to determine the maximum discharge of the rivers, and he proposed the formula which is Q is equal to 124A divided by under root of A plus 10.24 for all those areas which are less or equal to 130 square kilometers, and for more than that we have this formula. All right, and this formula is applicable to regions in Maharashtra and Deccan Plateau, to be noted. Maharashtra and Deccan Plateau. All right, So the key points of this English formula, let us discuss. Let us discuss the key points of English formula. Point number 1, it was developed by Sir Thomas Inglis. Developed by Sir Thomas Inglis. Key point number 2, applicable mainly to Maharashtra and Deccan Plateau. It's applicable to Maharashtra and other similar regions, particularly that of the Deccan Plateau. Alright, it is the next key point of the English formula. Third one being, it's used when flood records are unavailable. Used when flood records are unavailable. And fourth one is that it assumes average rainfall conditions. Assumes average rainfall conditions. Average rainfall conditions. All right. So this was about some of the key points of the English formula. The first one being, it was developed by Sir Thomas Inglis. The second one, that is applicable to Maharashtra and other similar regions, that of the Deccan Plateau. Third one, that is used when flood records are unavailable. And the fourth one being that it assumes average rainfall conditions. Let us study about its limitations. First one, limitations, all right? The first one is, it is not suitable for very large catchments. Not suitable for very large catchments. The second one being, does not explicitly consider rainfall intensity, slope, or land use. Does not explicitly consider rainfall intensity, slope, or land use. And the third one is that since it's empirical, all right, it's empirical, so the results need to be cross-checked. All right, so these were the limitations of the English formula. The first one being that it's not suitable for very large catchments. Second one, it does not explicitly consider the rainfall intensity, slope, or land use. And third one, since it's empirical formula, it's empirical, so the results need to be cross-checked. All right. So we studied about the empirical formula for determination of the maximum discharge of river. When we studied the Dickens formula, the Ali Nawaz Jung Bahadur's formula, the Rice formula, and the English formula, all right? But it should, however, be remembered that these empirical formulas are oversimplified and they give reliable results only if correct value of C is adopted. They give reliable results only if the correct value of C is adopted. And the reliable value of constant C can only be obtained by a careful study of the catchment area, isn't it? We can arrive at the reliable value of constant C only when we make a careful study of the catchment area with respect to flood occurrence, and that too for a long time. And it still is doubtful whether such a value of constant can be applied with success to entirely different region. All right. So the reliability of empirical formulas for estimation of maximum flood discharge is extremely limited in practical field, and the limitations, let me summarize them one by one for you. These are the general limitations of the use of empirical formula for determination of the maximum flood discharge. All right. Number one, let me write it down here. It is not possible to apply this method universally. A second one, they give fairly accurate idea about the peak flow for the catchment they represent. They give fairly accurate idea about the peak flow or the maximum flood discharge for the catchment they are devised for, or for the catchment they represent, right? They represent. Third one, it is very difficult to fix the constant or formula, and there is no exact procedure or theory for accurately predicting the value of constant. No procedure or theory to accurately predict the value of constant C. Fourth one, the empirical formulas do not take into consideration the frequency of floods. They do not take frequency of floods into consideration. Frequency of floods into consideration. All right. So these are some of the limitations. We have already discussed that these empirical formulas are oversimplified and they give reliable results only if correct value of C is adopted. And the reliable value of constant C can only be obtained by if we make a careful study of the catchment area with respect to flood occurrence, and that too for a very long time. And even after doing this, we are still doubtful whether such a value of constant will be applied to different regions or not. All right. So the reliability of empirical formulas for estimation of the maximum flood discharge is extremely limited in practical field, and the limitations are summarized here. First one, it is not possible to apply this method universally. Second one, they give fairly accurate idea about the peak flow for the catchment they represent. Third one, no procedure or theory to accurately predict the value of constant C. And the fourth one is that they do not take frequency of floods into consideration. So this is about the empirical formulas. All right, wherein we studied that how do we make use of certain empirical formulas to know about the maximum flood discharge. All right.